Okay, in this video we're going to look at another method for optimization problems. So when we think about optimization problems, the main idea is that we want to maximize or minimize some function. But the issue with these is these are what are called constrained optimization problems, so there is some sort of restriction on the variables. We actually already did some problems like this when we looked at finding maximum and minimum values of a function on some region, say on some triangular region. And so we actually already looked at that a little bit, but this is just another technique for handling part of that kind of problem. All right, so the theorem here says that we have an objective function. So this would be the function that we want to maximize or minimize. And in order to use this theorem, our constraint needs to be able to be written like this. So the idea here is that we have the same number of input variables. Notice here that I've got x1 through xn as my input variables, but this constraint or this restriction needs to be able to be written in an equation where that is equal to 0. So in essence, we're thinking about that restriction as a level surface of a function of n variables. When we go back and look at what we did before, essentially we would be looking at the boundary equations. So we would be looking at finding max and min values along boundaries. We did that previously using substitution. Substitution can work sometimes, but if you have a lot of variables or if the equations are kind of unwieldy, sometimes this Lagrange multipliers method is a lot easier to handle for those boundary equations. So this constraint, this is our restriction, and it's really a boundary equation. Okay, and so the conditions for the theorem say that if our functions f that we want to maximize or minimize, we call that our objective function, and our function g set equal to 0, so level surface of a function g, are differentiable on some open region containing the restriction or constraint, and the gradient of g is not the 0 vector. Notice that is the 0 vector there on that constraint. Then this theorem tells us that if f restricted to g equals 0 has an extreme value, so it doesn't guarantee that there will be one, but it says if there is one, then the point at which the extremum occurs satisfies this system of equations. So when you use this method of Lagrange multipliers, this system of equations is really going to be your workhorse and what you're going to work with to find the point at which the extremum occurs. So essentially this theorem tells you that this is the equation, or really system of equations, that you need to solve to locate the point at which the max or min value occurs. Okay, so when we look at this system of equations, let's just talk a little bit about that. So we notice that we've got two gradient vectors, the gradient of our objective function and the gradient of our constraint function set equal to 0. And then we have this other symbol here. This is a scalar, lambda, and really it just represents a scalar. So essentially the geometry of this is saying that these two gradient vectors have to be parallel to each other. One is a scalar multiple of the other. And in solving this system, we may or may not find what lambda actually is in this system of equations, but knowing about this geometry helps us to find the x1 through xn values that make this true. Sometimes students that have bad handwriting have a hard time using lambda because it looks a lot like an x or a y in their bad handwriting. So you can use some other letter if you want, c or k for a constant. It's just a scalar saying that these two vectors are parallel to each other. In a later video, we'll look a little bit at the geometry of why this theorem works and what it's really telling you about the geometry, and you'll be able to see those parallel vectors. All right, I'm going to scroll up a little bit here and we're just going to look at an example. I'm not going to actually solve this example in this video, but this is an example that I'm going to solve in a later video here, just so we can kind of get a feel for what these problems look like. This is a pretty simple one. We want to find a vector in R3, so we're going to have three variables, maybe we'll call them x, y, and z, with length 5. This is our restriction or our constraint, and the components should have the largest possible sum. So this is what we want to maximize. This is our objective function. And so if I write this out, we might say we're going to have a vector x, y, z, and the objective function that I want to maximize here, I want the sum of those components to be as large as possible. So I want to maximize f of x, y, z equals x plus y plus z. And the restriction is that the length of this vector is 5, so we might say that the square root of x squared plus y squared plus z squared equals 5, or we might choose to write that a little bit differently. But that gives us our g function. We would need to get that equal to 0, so it matches what we have in our theorem up here for our constraint function. Okay, when I do this, if I have a function of 3 variables, when we think about our little system of equations that we're going to have to solve, for one like this, where I have a function of 3 variables, I'm going to have the gradient of f equals lambda times the gradient of g. In essence, that equation right there can be rewritten as 3 separate equations. If these two vectors are equal to each other, then that means their components have to be equal. So we can also just rewrite that part as del f del x equals lambda times del g del x, and so on. So I often start with this system of equations, but you'll notice when I have a problem like this, I have 3 variables x, y, z that I'm going to be trying to solve for, and so these equations will involve x, y, and z. But then I also have this unknown scalar lambda. So at this point I have a system of 3 equations in 4 unknowns. A lot of students tend to forget the constraint as one of the equations in the system. So one of my tips for you when you're doing these problems is don't forget that you have the constraint equals 0 as one of the equations in the system that you're trying to solve. The other thing that you'll see when you look at some examples is that the algebra can be messy on these problems, and then you'll often use some algebraic techniques that might be a little bit different than you learned in a beginning algebra class when you were solving systems of equations. First of all, you'll have 4 equations or more and 4 unknowns. Also, just the way the equations can be structured often have some messy kind of algebra there. So just to really think through correct algebra and just to try to make sure that you're not doing things that violate the equality here. So just keep in mind that the algebra might be tricky and that that is normal for problems like this. The other piece of advice I would have when you solve systems like this and work on problems like this is that you want to be careful that you don't divide through by a variable that could be 0. So you need to be careful about the problem. On a problem like this, the variables would represent the components of a vector, and so those could be 0. If you're doing some kind of optimization problem where your variables represent maybe dimensions of a box, then you probably can't really have a box where one of the dimensions is 0. But you want to be careful not to divide through by variables that could be 0. The other piece of advice I would give you about this is that sometimes students solve this system of equations and then they just stop and put a box around the answer. If I scroll back up here to the theorem, it says if the function f restricted to g has an extremum, then it would occur at this point. So the other piece of advice is that at the end of all of these problems, you need to make sure that you remember to verify that your point really does maximize or minimize the function that you were looking for. All right, the other thing about this method is that it can be extended to more constraints. So this is an extension to 2 constraints. So we've got an objective function subject to 2 constraints here, both written as level surfaces of a function of n variables. So they're the same conditions really that our functions need to all be differentiable on some open region containing those constraints, and the gradient vectors for the constraint functions can't be 0. The other restriction here is that the gradient vector of the 2 constraints are not parallel to each other. Then it tells us that any points at which the extreme values occur are going to satisfy this system of equations. And so I just kind of want to emphasize what's different there. You've got a lambda and another scalar for the other gradient vector. So, and I have an example problem here for a problem that would be something like that. If we want to find a vector in R3 with length 5 whose components have the largest possible sum, that's what we looked at before. So our function that we want to maximize would be x plus y plus z, and then one of our constraints would have to do with the magnitude of the vector being 5. So we would need to translate that into an equation of x, y, and z equal to 0, and we'll do that in one of the later videos. And then the other constraint would be about the first component being twice as large as the second component. So we would say that the x which would be the first component of the vector, would be twice as large as the second component. So that x equals 2y, you could rewrite that as an equation involving x, y, and z. For this one, there isn't a z in there, equal to 0, and that would be your second constraint. And then you could do a problem like this. I don't believe there are actually any like this in your homework, but there are a few in the textbook if you look at some of that. And you should just be aware that you can extend this to more equations and more variables.